Good morning. Thank you for the Chappelle Natural Philosophy Society for having me here and for putting on this event. For those of you who know me, I'm generally very well prepared, or in my own mind prepared for talks. This talk I'm absolutely not prepared for. I don't know if I'm giving a 5-minute talk or an hour-and-a-half talk. If I see you nodding off, I'll know I'm going the wrong way. In the past 30 days, I've lost both my parents, and I've been dealing with that and working through that at the same time, trying to prepare for this event. So it's been rather interesting. I have a bachelor's of electrical engineering from Georgia Tech, and while I was getting that degree, I used to get into arguments with my professors constantly about special relativity and how it doesn't make sense. And being an engineering curriculum, I was just told, well, it gives the right answers to the problems. We don't worry about the physics behind it, and that wasn't very satisfying. But I did graduate, went to work in the Millstar Advanced Satellite Communications Program Office for the Navy. And I was up visiting my father one time, which is interesting because he, as a hobby, kind of studied relativity, and he says, I really don't get this length contraction and this time dilation stuff. So I drove up to visit him in Delaware at the time and said, well, don't look at it as length contraction and time dilation. Look at it as though light has some really weird property, and just go with it that way. And we drew some things on the board and talked for a couple of hours. And I realized leaving that the example I gave him actually kind of made a little more sense, at least in my mind, than relativity did. And so I spent the next few years working on that. During the course of my time working in Millstar, this new thing called GPS came along, and we were putting very small antennas on submarines that could pop up out of the ocean for a very short period of time, had to lock onto a satellite, get some data really quickly, and then get submerged again. So they did not have much time to figure out where a satellite was and how to lock onto it and how to get the beam pointed in a direction such that they could get the correct signal. So my job was to go figure out how to integrate GPS into this system. And I flew out to the GPS program office, talked to some people, and I had been taught that GPS was really new at the time, but I had been taught that GPS was a stellar example of special relativity and how special relativity works. And sitting there talking with the program people and some of the design engineers, I realized GPS doesn't really use special relativity at all. In fact, GPS at the end of the day shouldn't even work if special relativity is correct. They use some interesting tricks, the same as Felix Keating did, transferring all timing to this hypothetical center of the Earth frame. And I'm not going to get into that because that's not what my talk is about. But it spurred this interest back into me of what is special relativity. It doesn't make any sense. Nobody really uses it, except it does give good answers for Doppler shift, gives good answers for the slowing of clocks when they're put in motion, and good answers for some various things. So I went back and got a physics degree. I thought, okay, that electrical engineering is too practical, didn't give me what I needed to know, I'll go get a physics degree. Same problem with physics. In physics, special relativity is just accepted as a paradigm, like apples fall from trees, and it doesn't get questions, it just gets used, and then from there everything is built. And you can never question the axiom of special relativity, so it slows down physics in all kinds of areas. The nice thing, not the nice thing, but the interesting thing about my parents having passed in the past month is, while we're all sitting here wrestling with these issues, and we'll wrestle for years to come, they now know exactly what the situation is. They know how light works. They know whether special relativity is correct or incorrect, whether general relativity is correct. They know all the answers that we're going to struggle with as long as we're on this side of the Earth, toes above ground. But it makes me feel good to know that my father knows. I wish you could tell him, but here we are struggling. So what I've come up with, and I've been working this, presenting. A lot of you know me over several years. Published a lot in IEEE. Spoke to Russian Academy of Sciences and Queen's College in London. Is that special relativity gives the right answers. I learned that in engineering school. I learned that in physics. And yet there has to be a difference between the Galilean way of working things, or any of your all's way of looking things, and relativity. It can't give the right answers to every question, or it's a good theory. You just run with it. And so finally, in recent times, and I've spoken to Ron Hatch recently, But I came up with an example to use the very GPS satellites that tricked me up when I was a kid out of college. And I can use those now to actually test the relativistic simultaneity, which is the kingpin of Einstein's theories. Now Maxwell developed that the speed of light is given by this, these Pokemon go, they're going up everywhere. The speed of light is given by this equation, and basically the speed of light observed for any observer is going to be the same. It's going to be the same for any observer, no matter whether they're moving or standing still. Everybody's going to get the same value of the speed of light they observe, and Maxwell showed that, and that was pretty interesting. And that's a very key point. And I know that you can't actually go out and measure epsilon naught. You can measure mu naught, but the concepts are the same. I think there's some papers coming up on that. I'm not going to belabor that point. But since every observer is going to measure in their own frame the same value for epsilon naught and mu sub naught, they're going to get the same observed value for C, no matter whether they're moving with respect to each other or not. So all these different observers are intercepting light in free space, and they're all in motion, but every one of them gets a value of C in their reference frame. Now this is Einstein's original thought experiment with the train embankment. And what he showed was, or what he presumed was, if two flashes occur equally at A and B, that the moving train observer will see the light from B a little bit before the embankment observer at M. And we go on, and the observer at M will see the light from A and B at the same time, and then at some time later, the moving observer will see the light from A. So what we have here is the time of observing for M prime is different than the time of observing for M. So the two observers, the embankment and the moving observer, conclude that the events are not simultaneous. Events that are simultaneous in one frame, M sees the light from both flashes at the same time, are not simultaneous in the moving observer's frame. And I'm not going to give a whole lecture on special relativity, though I'm going to cover a lot of it here, and I apologize for folks who understand this completely, but I've got to drive to a point, and that's going to set up the experiment that I'm proposing. So we see that two observers that were initially coincident can't agree on the time of an event. But what I want you to think about is this point right here. So again, on the moving observer, we're going to look at that point, and we see that the distance from M prime to B is bigger than the distance from M to B. And we set the example in motion the same way Einstein did before, and now according to special relativity, this observer and the observer at M are going to see the light at the same place and at the same time, and this is interesting. Wow. So I don't know what happened there. But now you'll see that they're going to disagree on how far away the event occurred. And the reason this happens is because in relativity, the light moves at a constant speed of c in all frames, but with this weird twist that you have to look from this frame. You think light moves at the same speed, and something weird has to happen to this guy. It's very important to keep in mind here that MB prime is bigger than MB, and we'll see this later as we go along. I'm just going to leave that for a second. So in this particular example, and I'm not going to go through the math, but if the velocity was 6/10 the speed of light, then if MB was 3 light seconds, M prime B would be 6 light seconds, and the observer here on the embankment would say, no, actually your length is 4.75 light seconds. You had shorter rulers, and so when you put those shorter rulers into that length, you got this longer length. Same thing with the time. Your time is dilated, and again, I'm not going to belabor the point of those equations. You can look them up anywhere. But now we want to go back to this example where we've got Alice stationary and we've got Bob stationary, and light travels from the source to the observer in a time given by the distance to the source at the time of emission in the frame of that observer divided by c. It's very simple. We have a flash. Bob sees the event. Alice sees the event, and t prime is greater than t. Why? Because Alice is further away than Bob. Nobody is going to question this in their right mind at all. So now we look at Bob seeing an event all by himself, and it doesn't matter what the speed of the source is. We have a random source traveling through space, and suddenly it emits a photon, and the distance to the source in Bob's frame divided by the speed of light is the time it takes light to get there. There's nothing magic here. We look at the same event now where we have Alice just kind of cruising along. We don't really care about Alice because we're just looking at Bob, and nobody's going to question that Bob is going to see the light at a time given by t. And hopefully the screen will come back on and we'll be able to continue. Okay, so we can look at the same situation with Alice where she has a length d prime, and boom. And we can also have Bob kind of wandering along. Flash occurs, and Alice sees it at a time t prime divided by c. No, nothing magic here. Nobody's going to question this. We can look at both of them at the same time, and nobody's going to question the times here. T prime is greater than t, period. But now, something magic happens. We put the two of them together, and we do the exact same event, only now people are going to disagree that t prime equals d prime over c. And you're going to say, oh, you've changed the situation. Alice is moving. So clearly things have changed. Bob is stationary, Alice is moving, so you can no longer say t prime equals d prime over c. But if I put myself in Alice's restaurant frame, then you're not going to question that t prime equals d prime over c. So nothing's changed here. In this reference frame, you're not going to disagree that t prime is d prime over c, and up here you're not going to disagree that t equals d over c, and you can't consistently say that either one of these situations is wrong. So t prime is greater than t. All we know is that the time is given by the distance to the event in the reference frame of the observer divided by c. And that's really all we know about light, is that it's observed to have the velocity of c in my reference frame as the observer. And I can even put myself in here as a disinterested third party at some point where both have motion, and it's again going to be the same situation. Now that's what I've just explained to you is Galilean relativity. We're taking Maxwell's velocity of light equation, and we're taking Galilean framework, and that's the top frame. Now what special relativity said is, if you remember from the first slide where I said, remember that point where the two observers see it at the same time, relativity says these two flashes are going to reach both observers at the same place and at the same time. And in order for that to happen, since d prime divided by t doesn't equal c, then t prime also cannot equal t. So that initial assumption that Einstein made, that the two flashes are going to arrive at the same place and the same time, leaves us with a problem, and that it can't be correct. This length cannot be d prime, that time cannot be d prime, t prime, and also have them see the event in the same place and the same time. So, let's see what slide we got on here. Okay. So the way relativity fixes this is they come up with this arbitrary constant, gamma, and we're going to derive this in a little bit. And they say, okay, as I showed before on the train embankment screen, Bob says, Alice, all your rulers are shorter, so that what you think your length is just completely wrong. All your clocks have slowed down, so what you think is the time is completely wrong. But when you make these magic adjustments that I'm proposing, suddenly you have a new length and a new time, and your d prime bar over t prime bar equals my d over t, and the velocity equals c, and we're all happy. Everybody gets to see the flash at the same time. And in the example I'm giving here, or the one I gave on the train embankment, if the velocity is 6/10 the speed of light, and Bob's length is 3 light seconds, Alice thinks her light is 6 light seconds, but Bob says, no, it's really 4.75 light seconds. You measured it with a shorter ruler, so you got more rulers in the space. And again, the same thing with the clock. So we have to ask, how did this happen? How is it that relativity gives the correct answers so often when it seems to be just insanity on the face of it? And Peter Beckmann, who is the original editor of Galilean electrodynamics, came up with a great theory. He came up with the grand railway theory, or railroad track theory. And he proposed that lengths shorten with distance. And he said you can test this by looking at a railroad track receding into the distance and see that the farther away it gets, the closer the tracks get together. Therefore, it's proof that the that distance shortens with distance. And he said if you run down to the tracks with a ruler, you're going to measure the same width you do up here, but you've changed your reference frame. You're now at that distance, so that rules don't apply anymore. It's only things that are far away from you that have a shorter distance. And you can develop a completely consistent mathematical framework based on that assumption, which is going to give you all the same answers that an increasing field of view does, and what we know to actually be the case. So we call that an equivalence. And what we have with special relativity, for the most part, is an equivalence with the Galilean way of looking at things. And so what we're going to try and do here is, starting with what we know about the Galilean transform, we get to the special relativistic transform and say, this is how we came up with this nonsense, and this is why, for the most part, it gives the right answers. And I'm going to do that briefly here. I apologize for the math on the screen. And nothing happening. Okay, so given this event that we've been viewing the whole time, where we're agreeing that Alice sees what she sees, Bob sees what he sees, we start with Maxwell's light speed equation. We have the time that Bob measures, we have the time that Alice answers, and we have the famous Galilean transform that everybody knows and loves and is familiar with for throwing baseballs at cars and snowballs and things like that. So when we take these equations, we can now say, we can take this equation for x and do the substitution for t prime, and we get x equals x prime 1 minus v over c. Now we can rearrange these terms a little bit to solve x prime in terms of x and t. And it's very simple math. I'm not going to go through it, but I've introduced this term gamma, which is, this becomes gamma 1 over gamma, or this becomes gamma squared. This 1 over this term becomes gamma squared. So I can rewrite x prime in terms of this gamma squared of gamma squared x minus vt. There's nothing interesting here really. It's still the Galilean transform. Since I've introduced this crazy term here, I have to be careful that v never equals c, or the whole thing blows up. So except for that one point, this is a completely valid Galilean transform equation. We'll take out the derivation and just leave the x prime. Likewise, t prime equals x prime over c. And the reason the minus sign arrives here is because we're looking at the time that we observe it as 0, and the time of the event would have been some time before then. So it's the time of the event, not the time of observation. It doesn't really matter, it's just a convenience. So substituting this value for x prime and carrying through, we get t prime equals gamma squared, and taking out the derivation, we have this wonderful term. So now we have x prime and t prime in terms of x and t and the speed of light c. This is still the Galilean transform. I haven't done anything at all here except that I introduced this term and then multiplied it through for simplifying things. But now Einstein, this is the Galilean transform still under our assumption that Bob sees the light when he sees it, Alice sees the light when she sees it. But Einstein said, I'm not happy with that. I want them to see the light at the same place and at the same time. So what he did is he divided both, and this is not how Einstein developed these things. Don't misunderstand me here. I'm just getting to the same equations conceptually as to how this, what special relativity is actually saying. He divided both of these equations by gamma and defined a new term, x prime bar, which is x prime over gamma. And since I've divided through by gamma, I'm now left with gamma x minus vt. Did the same thing with t prime. Divided through both sides by gamma, nothing wrong with that, except you have to make sure you're not dividing by 0 anywhere. And you come up with an expression for t prime. So these are now the special relativistic transforms. So what have I done here? I've done nothing. I took the Galilean transform, created this interesting term that serves no purpose except it helped me simplify some of the fractions that I was coming up with before. And now I have these new expressions for x prime and t prime bar. And what these expressions allow me to do is within my frame, if I'm Bob, I can look at what's going on in Alice and I can take the ratio of these two to get the speed of light. I can convert from my frame to hypothesize what might be going on in her frame and then convert back to my frame. But what I can't do is say that her length is really x prime bar and her time is really t prime bar. That's a fallacy, because all I've done is play around with these equations and divided through, and everything I did was ratios to begin with, and every answer I get has to be ratios, otherwise I'm creating something that doesn't exist. If I say, for example, that 8/4 equals 6/3, that's great. But I can't then say that 8 equals 6 and 4 equals 3. That's a fallacy that just makes no sense and falls apart on the face of it. So by having done this, I can now look at this experiment and say, oh, Alice and Bob see the event at the same place at the same time, but unfortunately they can now no longer agree on when the event occurred or where the event occurred. They now have a lack of simultaneity. What was simultaneous in one frame is now no longer simultaneous in another frame. So this is, again, it's algebraic manipulation of the Galilean transforms. There is absolutely no physics in this derivation, and Einstein's assumption that they see the event at the same place at the same time, the relativity of simultaneity, has never actually been tested. So now we're going to figure out how can we use the fact that this hasn't been tested, how can we develop a test around this? And we're going to look first at the special relativity piece down here. We launch two waves, and we pick a point, say the peak of one wave. Now we saw from the earlier slide of the train embankment and from this slide and from the other slides that that point, if it arrives at the time when Bob and Alice are co-located and Bob observes that point, then Alice is going to observe that point at that same time. And it doesn't matter if it's a point, it can be the peak of a wave, it can be the rising edge of a timing signal in a satellite signal, it can be, you know, the first note of Born to Run by Bruce Springsteen on an FM signal. It doesn't matter. The point is, whatever happens at Bob is going to happen at the same instant at Alice. There's going to be no phase difference. And here we go with the screen again. So looking at the same situation from the Galilean relativity, and we saw this before and we know what happens. Bob sees the event sooner than Alice does. This point has yet to reach Alice. By the time that point does reach Alice, Bob is now seeing a different part of that wave, and it's either a different part of the signal, a different node of Born to Run, a different position on the timing signal. In any event, there's a phase difference here. And for a satellite at, say, 20,000 kilometers, which is where the GPS tends to hang out, and a velocity of about 10 meters per second between Alice and Bob, we're looking at a time delay here of about 5 times 10 to the minus 9th seconds. Not a big difference, but an easily measurable difference, especially when we're dealing with signals and phase delays. So we need to come up with an experiment that's going to allow us to test, is the Galilean picture of things correct, or is the relativistic picture of things correct? Do these signals arrive in both frames in phase, or do they arrive in both frames out of phase? And how can we do that? Well, a top-level conceptual diagram, we'll use the carrier signal of GPS, and Ron's back there shaking his head going, you can't use the carrier signal for GPS because it's differential phase shift key and broad spectrum and all that. So this is conceptual. Imagine we have a satellite that's doing nothing but putting out a 1.575 gigahertz carrier signal, and it's raining outside, so we're not actually getting that signal. Here it goes. Okay. So we have a mixer here that's going to receive this GPS signal, and then it's going to provide that signal to a phase lock loop, which is going to generate another signal. And this transmitter is in the lab frame. It's about 10 meters, 50 meters away from this detector. And we're going to take both these signals, we're going to mix them together, and we're going to put an output. That if the two signals are exactly in phase, the output's going to be 0. And if the two signals are out of phase a little bit, we're going to get a voltage proportional to the phase. This is electronics 101. We also have another identical mixer on a track moving at a velocity v towards the line of sight of the satellite. Well, this moving frame is going to pick the satellite signal, but as we saw on the previous screen, it's going to get a given wave peak at a different time than the lab frame is going to get it. And yet, this device, which is in the same frame, is only about 10 meters away. That signal is going to arrive at the same time that it does in the stationary frame, because we're talking about a time difference here on the order of 10 to the minus 17th. We can just ignore that, because we're not interested in measuring anything below 10 to the 9th, 10 to the 10th. So there's going to be a phase difference here due to the fact that it takes, in a Galilean framework, longer for this signal to reach this mixer than it takes the signal to reach this mixer when they're co-located. And the output of this phase detector is going to be different than the output of this phase detector, and we're going to be able to say, aha, for a given speed, the phase shift in the moving frame is different than the phase shift that we get in the laboratory frame. And if we perform that over a lot of different velocities, a lot of different directions, back and forth, we can build up a map and say, yeah, there's very strong evidence that the phase difference is tied to the velocity of the moving system, and we can plot that out within the error bars. And it's very interesting that 5 times 10 to the minus 9th is about the same criticality of the clock jitter and the GPS and a bunch of other factors, but everything can be overcome quite well. I'm not going to bore you with the details on that right now. So looking at this time delay equation for the GPS satellite, the time in the lab frame is ds over c, ds is the distance to the satellite, and in the moving frame it's ds prime over c, where ds prime is the distance to the GPS satellite at the time of emission as measured in this frame. So we're going to have Alice be co-located with Bob at the time the signal reaches here, but the time is going to be longer because, as we saw, in all those slides before. So ds prime from the Galilean example is ds plus vts. Even if we used special relativity, it would be the same because the velocity is 10 meters per second. We're not doing any high-speed relativistic travel here. So doing a little mathematical manipulation, we get that ts prime is ts times 1 plus v over c. So the difference in time, which is the phase shift, is going to be ts times v over c. And again, we're in the order of 10 to the minus 9 here. Likewise, for a lab-based signal, if we have the signal starting about 100 meters away or less, the time difference is on the order of 10 to the minus 17th. We could ignore it. We're not looking for anything below 10 to the minus 10th. No, it's going to have no impact on the results. So for all intents and purposes, the lab-based signal is the same in the moving frame and the stationary frame. It's getting more. So, okay. So here's the time delay that we're seeing.
Is your battery charged?
Yeah, no, it's an Apple problem.
No, it's actually, the apple's completely on, good to go.
Oh. My Apple just goes down like that.
I think it's electrical engineering, it's a certain amount of software problem.
Let's see if we get okay. Now, there's two ways to look at a GPS satellite. One is, not that way. One is to consider a satellite that's on the horizon, and one is to consider a satellite that's directly overhead. We could do the experiment either way. But what we're really interested in is looking at a satellite on the horizon for a bunch of reasons. One, it's much further away, therefore the time delay is bigger. Number two, since it's on the horizon, I can have my moving frame moving across a lab instead of having to go vertically up and down. And it's just a lot easier experiment to do. But I also looked at what would happen if we were to do it overhead, and like Pound and Reb could just drop a receiver down the Harvard Tower. But for looking at the horizon at a speed of 2 meters per second, we've got a timing difference of 5 times 10 to the minus 10th, pretty small. Moving at 16 meters per second, which is easily doable. We're looking at around 5 times 10 to the minus 9th seconds, which is a very healthy difference, and we can measure that. So if we were to perform the experiment at all these different velocities and even higher, we would get a plot like this. And of course, with the error bars of the noise and everything going on, that's going to jump around. But if we start seeing this trend, special relativity would predict 0 for all speeds, whereas the Galilean form and several of the other theories out here are going to predict this type of curve. And actually, some of the other theories out here would also predict 0. So this is a test between special relativity and a strictly Galilean framework, not necessarily a test between special relativity and some of the other proposals that I've seen out here. So the GPS signal has a coarse acquisition code. 1 megahertz, Ron, is that?
10 megahertz.
You're
one
you work with the real signal. Yeah, the military fine acquisition code, the precision acquisition code is 10 megahertz, which would be great. But using a 1 megahertz code, that's going to get
Kurt, let me mention that,
Yeah.
in fact, most of my patents have to do with carrier phase. You can pull the code off
Right.
and get at the carrier phase immediately.
perfect.
So-
And Ron's got exactly what I'm looking for. So we showed earlier we're looking at a phase difference, and we're going to put a voltage out according to the phase. Well, practically we can't do that. But what we can do is take this coarse acquisition code, which is just essentially a square wave signal being broadcast from the GPS satellites, and it's a pseudo-random code. Each satellite has its own unique code. So in the Did I put the example again? Okay, so if we start with our lab reference and it's got its own pseudo-random code, and the GPS signal has a code, then if we sum those together, we're going to get an output that looks something like this. In the moving frame now, where there's been a delay in the course acquisition code, we're going to get a different sum. And by comparing the two sum signals, we can measure the time, the 5 times 10 to the minus 9th time delay is shown in the difference of these two sum signals. And this is very easy to do. It's not complicated. You can buy off-the-shelf equipment. You used to be able to buy it at Radio Shack. You can buy it at Fry's Electronics. Now you can build this pretty simply. So here's a block diagram of the conceptual idea put down into an actual experiment where we have a GPS satellite sitting on the horizon sending out its course acquisition code. We have a lab-based source, and for convenience, we'll put that up around 1 gigahertz, 1.2 gigahertz, just so we're in the same realm. And it's also putting out a 1 megahertz or so course acquisition code, or if we can use the precision code, 10 megahertz, which gives us better timing. We receive both of these signals. We collect the time and range data from GPS just to have for historic to look back and make sure we're not doing anything stupid. But mainly we're going to store the course acquisition code, we're going to store the reference code, we're going to store the sum, process and do whatever data reduction we need to do, and then put it on a mag tape or punch cards or whatever we want to store it on, probably volatile RAM. We have the moving frame, which is exactly the same setup, except it's getting a time-delayed signal from the satellite, or if we believe in special relativity, it's not getting a time-delayed signal from the satellite. And again, we take the sum and we process it. And then after the experiment's done, we take our data out of here, do the data reduction, do the plots, and hopefully come up either with the graph we saw before or with a straight line graph. Now this is pretty easy to do. And I've actually got a company out in California that's working on this piece of things. But as I was looking at this problem, I realized I don't need a reference code generator. I have plenty of reference code generators. Namely, if I'm looking at one GPS satellite on the horizon, I've got another one in the same orbit, almost directly overhead. And I can use that pretty much as my reference generator and get rid of this equipment and use just a GPS processor on this equipment. It makes the construction simpler, makes the error sources smaller. And the way that works is this. We've already seen that the time delay for the satellite on the horizon is given by TSV over C. For the satellite overhead, DS2 prime is just given by the Pythagorean theorem, where we've got VTS1, which is the time for the moving frame to move this small distance. We're talking about 1/10 of a second for the signal to get from the satellite down, so it's a very small motion. And we can say that DS2 prime equals DS2 on the order of, again, 10 to the minus 17th. Just to be conservative, I said on the order of 10 to the minus 15th. This distance is in the noise. It's way below the level of the signal that we're looking for, and we can ignore it. Likewise, the time of travel divided by C is on the order of 10 to the minus 15th, and we can ignore it. So we can use a second satellite as our lab-based generator and not have to worry about creating this generator, creating a pseudo-random code, and doing all that hardware. We've already got it up in space. So this is the same block diagram we saw before with the two satellite approach, where we've got the satellite on the horizon, which is really our test signal. We've got the satellite overhead at zenith, which is our reference generator. We have identical processors. We're going to go ahead and pick up ephemeris and time and range data for both satellites. And the reason we do that is because there is a little bit of Doppler effect that we didn't have to deal with in the lab-based generator because the signal was going on the same path, and I forgot to discuss that. Needless to say, it's in the paper and it works out. But we've got two identical receivers. We're collecting all the data. We're collecting the actual course acquisition code from the horizon satellite, the course acquisition from the satellite overhead, the sum, and then we've got our moving frame collecting all the same data, doing the storage, running it multiple times, different directions, different orientations. And the nice thing is we don't even have to keep the lab frame stationary. We can run the lab frame in the opposite direction and essentially double our speed and get all kinds of different effects. But this is the basic equipment. And GPS processors exist off the shelf. Obviously, you've got one in your phone. As Ron said, he's got patents on equipment that'll pull the CA code out, so that's not a big deal. summing square waves is trivial. Anybody that's got an EE degree did that in their first year of electronics. And of course, processors and storage are abundant. So it's very simple, easy to do. And this is a proposal that I'm currently submitting to both DARPA and to the National Institutes of Standards and Technology to try and get a little bit of funding to perform this. But even if I don't get the funding, the more I work on it, the more I realize I can probably self-fund this and get the project going, and we're looking at possibly doing that. So that's I think that's the one. Yes, so that's it. And I'll take questions. I'm going to pull this back up because we need to go to the slide. Yeah. So questions?
Have you considered using Kickstarter or other crowdfunding?
Yeah, it's interesting. There's actually crowdfunding for scientific experiments. I was surprised. I just found that the other day, and they tend to be in the $5,000 to $10,000 range. We're a little bit higher than that, I think, for some of the equipment, and just having some grad students running around. But yeah, I've looked at that, and again, hopefully our own company can be able to fund this. And Steve.
So a couple of comments and a question. So first, I'm sorry to hear about your
Thank you.
condolences there. Can you go back to your slide where you establish X bar?
Answer your question? No.
Okay, well,
No, of course I can. It's right. Oh, the one where I developed it, so it's the derivation screen. Here we go. Correction and derivation. Here we go. So this is the Galilean transform, where I just randomly introduced this gamma term. There was no reason to introduce it, but it allowed me to get rid of some of the 1 minus b over c that you can't help but get in a Galilean transform. And then from there, I just divided both sides of both equations by gamma to get the x prime bar and t prime bar.
Okay. Thank you for that. And then the last one on your picture where you have the two satellites, I mean, the imagery to me, and it just kind of spun up the name as and maybe correct me if I'm wrong, but it feels like a satellite interferometer experiment.
Exactly. In fact, it pretty much is. And in the paper, I mentioned the LIGO interferometer, which is kind of interesting as well. But yeah, it basically is an interferometer, but unlike the interferometer, which is like Michelson-Morley, at the end of the day, is doing everything in one frame. So if you're sitting with the Michelson-Morley interferometer, or the Michelson-Miller, or the Michelson-Gale, which is it's just a test of projection of spherical coordinates onto rectangular coordinates, it's neat. But it's really still the Michelson-Morley experiment. If you're in the frame of that equipment, nothing's moving, period. So in the frame of that equipment, you're stationary for the entire experiment, and all you're testing is sending a signal in a stationary frame down two arms of an equipment, and you shouldn't expect to get any variance whatsoever. And of course, we don't see that, notwithstanding your results, which I have not reviewed. So, Ron.
I would encourage you to look at the GPS spec for a moving receiver. 200D specifies that you are to compute the range from the satellite to the position you're at the instant it's received. In other words, they specify that a moving receiver make the measurement exactly the way you're saying. Mm-hmm. So the only way they can get a proper answer is to adjust for exactly what you're specifying.
Yeah, and that's correct, and that's why I feel pretty confident about the results of the experiment. And Ron and I talked, and he said, yeah, those are the results you're going to get, and they're going to ignore you. and I think that's probably true, because you look at experiments that have been done out there, especially in the quantum. We were talking before about the quantum experiments. Every quantum experiment out there shows that there's instantaneous communication between events, and yet every result you say says this doesn't violate special relativity, however, and then they go through cartwheels to explain why that's the case. And it's it would be so much easier if people could just say, okay, there's something wrong out here. Let's take a look at all the experiments we've got, all the evidence we've got, and maybe relook at this paradigm that we've been carrying around for 105 years, 110 years. Yes?
Yeah, I was just going to agree with you, just what you just said, the last 10 seconds. The thing, I'm an emission theorist, and what I've done, I've assumed that you have a primary photon, a primary wave packet, and in the observations on it, you can show why the mainframe cannot measure velocity of a primary photon. It's minding its own business out in space. You can be moving with 10 times the velocity of light, but to make a measurement on it, you interfere with it. And it's a primary thing. In order to measure velocity, you have to have 2 points, x1 and x2, and you got to have 2 times, t1 and t2. Once you make a measurement, you've already interfered with the primary. You killed it, right? And what you got, when you place a lens in front of it or a window, and what interferes with the boundary of the window propagates within the glass or whatever that comes out the other end. That's a different photon. It's not the same. It's a different wave pattern. Exactly. This is H2. So you killed X1, and H2 means nothing because you can measure neither the velocity nor the wavelength. So I've done a similar calculation to what you've done. Matter of fact, we agree 101. You had used for example, you have the transverse relative time shift. The transverse relative time shift is the inverse of the transverse relative frequency shift. And I think we agree we're doing the same calculation. Yeah. But I'm an emission theorist. So you have to believe in emission theory. Yeah. And hold it. You do all this calculation for that relativity.
Yeah, in fact, that's so critical that a photon, if you think of it as a quintessential quantum wave packet, if you're going to say where you're going to detect it, then you can't say anything about the time you're going to detect it. In fact, any observer moving at any velocity can pick up a photon at a specific place, assuming their relative velocity is correct.
Right.
Likewise, if you're going to get a photon at a specific time, you can get that photon anywhere in space, again, assuming that the relative mover has the correct velocity. And to challenge that is to challenge the very underpinnings of quantum mechanics itself. So you can't say that photons are different than every other quantum particle and that they have a specific place in a specific time, and every other quantum particle, if you know with precision the place, you don't know anything about the time, especially when C factors into every one of those equations. So thank you.
Yes, I don't know whether I get you well. Are you dismissing the principle of constancy of speed of light, irrespective of the motion of the observer? Dismiss that.
The constancy of the speed of light with respect to the observer is always going to be c, based on Maxwell's epsilon naught view in free space and given what we know about material science.
Yes, that's c, a number.
Yeah.
C.
Mm-hmm.
But as distance covered over time taken, is it constant?
It's not constant. As we saw, different observers at the same place will see light from a source emitted at a specific time at different times. And the reason this is extremely interesting to me is because if I can show that I can get the light, the GPS signal, at a different time at the same place from two different observers, then I've shown that light essentially has components all the way from 0 up to whatever speed you'd like. Now it becomes an engineering problem, and engineering is what I do. I go to the material science guys and I say, look, I don't want to have a moving observer moving at 6/10 the speed of light to get this signal. I want to be able to get this signal here. Develop me some materials that are sensitive to the higher components of light. And if I can get the materials guys to come up with components that are picking up the light that's traveling at 2 times c, or 3 times c, or 10 million times c, suddenly I can get instantaneous communications. I can control space probes that are out at Pluto as if I'm controlling a drone flying over my head. Or if I'm at alien civilization communicating with other alien civilizations, I can do that instantaneously. I don't have to wait hundreds of years to get a signal back and forth. And it along those lines, and I wasn't obviously deviating from the topic of this meeting, but if I'm an alien civilization who never had Einstein, and never created this artificial speed limit. And we went off and developed communication systems that can communicate instantaneously across any distance. And I'm pinging the Earth with signals all day long going, it looks like there's life down there. It looks like they're intelligent, like they have technology. And yet they never answer us, and they never acknowledge that they're getting our signals. That's because we're like listening for drum beats in New York, going, oh, there's no intelligent communication there because nobody's communicating by drum beats. No, they're using cell phones and satellites, and the aliens are looking at us going, I don't know, those people are just really stuck up down there. So. Give one more.
Yeah, this whole thing of light is interesting to me because the Greeks had already, by 300 BC, had already had these three schools. And there was a school, the source school, right, like Edward there. And then there was the medium school, Aristotle, and then the ether guys, and then there was the Einstein equivalents of the receivers. So when I went through setting up an experiment like you did, and what I realized what would be helpful is if the experiment could test all three for all three at the same time. And you only have to make one or two additions. So I think what was helpful is I'll look at your paper because I was reading it and make some suggestions. But just when I explain to you what I'm thinking about, you might then be able to incorporate that. So when you come out, instead of saying, well, we disproved Einstein or we disproved relativity, you came out and say, the results say it's a source-driven problem, or it's light is a medium-driven phenomenon, or it's a receiver. And most likely what we're going to find out is that we don't know what we're talking about even with the three of them. We've got to learn something new. As you said, there's higher levels or something.
I agree. There's a more that we don't know than that we do know. There's no question.
Well, last question.
I've got one more thing. One more thing that's very misunderstood by a lot of communities here in national and international, and misunderstood. And that is two words: the velocity of light constant and the velocity of light constancy. They mean two different things. The velocity of light constant, that is the value that you get to carefully measure the velocity of propagation of light in a frame of reference where you would the source and the observer is in exactly the same frame. They're not moving relative to each other. But however, if you let one move and the other not, the velocity of light constancy refers whether the Galilean transformation of velocity is correct or not. That's the difference between the two. And a lot of people get those two things confused.
Okay, thank you.